Thanks, Rhiannon, for the kind introduction. And thanks also to all of you, Simon, Rhiannon, and Vincent, for the nice opportunity to talk to you about my works that most of them were indeed performed in the Surface Science Laboratory here in Darmstadt. And I will obviously talk about solar cells, perovskite solar cell, but especially about how to probe interfaces with photoelectron spectroscopies. So first of all, maybe a few words on photoelectron spectroscopies, just that we all know the basics. Photoelectron spectroscopies is based on this photoelectric effect, where you send a photon, and if you have enough energy, you will extract some electrons and put them into a vacuum with a given kinetic energy. And if you put a detector here, you can measure this kinetic energy. You know the energy of your incident photons. So if, for instance, you do XPS, you have photons, X-ray photons. If you do UPS, it's for ultraviolet photoelectron spectroscopy. So knowing this, measuring that, then due to the conservation of the energy, you can calculate binding energy of your electron to orbital of different elements inside your material. And because all these binding energy are more or less known, you can then say, okay, I have this element inside my material. You can know some oxidation state of your element. And what I want to talk more today is that you can measure some electronic, energetics properties of your material. There are two things I would like to stress. Photoelectron spectroscopies are a surface sensitive technique. The main reason is that, of course, your X-ray can penetrate quite deep inside your material, but the main limitation is that the photoelectrons you create have trouble to escape from your material. This escape follows the Beer-Lambert law, which is depending, of course, of the z-axis. Where does the electron come from? Your angle here between the normal of your sample and the detector. And this parameter, which is inelastic mean free path of your electrons, and this depends on the kinetic energy of your electrons. So if, for instance, we use XPS, so standard X-ray with a photon of roughly 1,500, then you will create electron with a kinetic energy at the best at 1,500. So you will measure in this range, and the experimental inelastic mean free path says that it's around 2.5 nanometer. So then, because of the Beer-Lambert law, most of your signal will come from this 2.5 nanometer of thickness, and you will go at the best to something like 15 nanometer, which is roughly what you do with XPS, and which is even more close to the surface when you do UPS. So it means that you cannot really measure your sample, I mean the absorber of your, for instance, perovskite solar cell, because you have all the thickness, you have your contact material and so on, and you will not access, let's say, the absorber. So another way would be to get this normal cross-section with FIB, for instance, and to measure from that. But the second issue with the technique is that the lateral resolution is at the best 1 order of magnitude higher than a standard thickness of your sample. So you will not be able to distinguish the different layer of your perovskite solar cell. So if you want, you can use other technique, of course. You can use a Kelvin probe force microscopy, which is more resolved, and then you will get some nice electronic information. You will measure the work function of your different material across the cross-section. You can also do microscopy, and for instance, EDX, and you will get chemical information on your different layers. But to the best of my knowledge, photoelectron spectroscopy is one of the most common technique to access both electronic and chemical information at the same time. So if you really want to use a photoelectron spectroscopy on layers of your perovskite solar cell, you have to find some tricks. The most obvious one is to measure the material separately. So you first measure material A, material B, and then you do some hypotheses what it should behave when you put them together. So that's what we did in a collaboration with some people in Munich. So Maximilian came with this work where he has some lead-free perovskites, and he found out that when you put phenetyl ammonium bromine, which is used as a spacer, you will create a 2D perovskite on top of your 3D. So you will get a 2D, 3D hybrid perovskite solar cell. And he wanted to understand a bit what was the influence on the electronic structure of this device. So of course, first, XPS, you can probe some elements. So as I said, the binding energy are quite well known. So here you have a survey spectrum, and if you have some peaks at this binding energy, you know that it's bismuth. Here it's cesium, so you can say, okay, I measure the lead-free perovskite that I'm supposed to measure. And what was interesting was to see that when you look at the core level nitrogen 1s, this orbital, you get some electrons coming out in the case of the 2D, 3D hybrid, meaning that you have nitrogen, and this comes from the spacers that you put here, the nitrogen atom. So that was one additional proof that on this sample, you succeed to have this 2D layer. And then for the energetics, well, we measure, of course, other core levels, such as bromine, and we also measure the valence band edge of your materials. And you can see that when you have this 2D layer, well, you observe a shift to lower binding energy. Another way to say it is that it's closer to the Fermi level. And that gives you some information on the electronic structure. Because your Fermi level here at zero binding energy is, of course, the one of your sample, but also the one of your machine, because everything is aligned, everything is in contact. So you have all your Fermi level aligned, and then you can measure everything relatively to this Fermi level. And here I measure a valence band edge at 0.5 for the 2D, 3D hybrid, and a bit below for the 3D pristine material. And you can also observe these shifts on the core level, because there is no reason why the distance between this core level and the valence band edge should change. So you have a shift of all your core levels. Then you can, of course, also with XPS or UPS, you can measure the cutoff, which is basically the last electrons that you can measure. And this leads you to the work function. So you can then position your vacuum level, and you can, of course, combine photoelectron spectroscopy with UV-vis absorption spectroscopy to get the band gap of your material, and you are then able to draw this band diagram. And you can do it for the perovskite absorber, but you can also do it for the whole extraction layer. And here you see I was able to put the valence band and the conduction band of the spiral myosad. And what you can then conclude is that when you create electrons and holes inside your 3D layer, then you can easily transfer the electrons to the spiral myosad, and here you have an additional blocking layer that prevents the electrons to go from the absorber to your whole extraction layer. And that leads to an improved selectivity and an improved efficiency of your solar cells. So of course that's lead-free perovskite, so the efficiency is not so high, but you can see and improvement of your solar cell. So I don't want to spend too much time on it, but just to mention that I worked during my PhD on other solar energy materials. I worked on photocatalysis, and I did similar study with using UPS on powders this time to study titanium dioxide and the transition metal sulfide that I support on it to produce hydrogen. So I used this material to do some photocatalytic production of hydrogen. And I used UPS to measure the valence band edge here, and also to probe some valence band states inside my powder. And this helped me to then understand also some mechanism during photocatalysis. So photoelectron spectroscopy is quite a technique that you can apply to in many fields. So if you're interested, we can talk more about that, but I'm now coming back to a solar cell. So as I said, this is the most common technique and the easiest one. Everybody can use it as long as you have access to a XPS machine. But the main drawback is that then you need to do some hypothesis to what is happening at the interface. And if, for instance, you have some chemical reaction at the interface, then the interface energetics are completely different. So to do that, you have another strategy, which is basically to grow some interface directly in a machine and to analyze it with photoelectron spectroscopy. And for that, you need such a system, an integrated system that in Darmstadt we call DAISY-SOL. You have here the analytic chamber, and then you can go and prepare whatever you want inside your machine, like perovskite, or you can go in some organic chamber to put some oil extraction layer. And then without having atmosphere exposure, you can measure directly your sample inside the machine. And this leads to what we call interface experiment. And this is highly reported now in the literature since decades, and this is really what was done in my group for decades. So let me explain it a bit. You start with one material. So in my case, that was methylammonium lead iodide. And here I show you the nitrogen 1s core level spectra. And you can see here a characteristic peak of this MAPI layer. I will then add a really thin amount of spiral. And as I said, you can probe a depth of roughly 10 nanometers. So if you put only 1 nanometer of material, you will obviously go through the material and you will detect both the spiromyosad and the MAPI layer. So you have this new feature here that belongs to the spiral. And then you will slightly increase the thickness until you see MAPI that completely disappear and the spiral that is rising up. And again, you can check the binding energy shift of your different peaks. And here you can see that if you follow the spiral peak, you have a shift to lower binding energy of 0.3 electron volts. And this indicates a band bending at the interface of your material. So when you're far away of your material, you are 0.3 electron volts off the reference binding energy that you measured when you were at the interface. And you can use other core level to probe that. And it's the same with the carbon 1s peak. You also observe a shift. And you can also do it with the core level that you should observe inside your perovskite layer. So this time you probe the iodine peak, and at the beginning you have a strong intensity until it completely disappears because you're only measuring spiral. And this time you can see a shift of 0.1 electron volt, which is the same as you observe here. And this indicates you the band bending of your material inside the MAPI and inside the spiral. So you can then draw such a band diagram. So with the core level, you draw the band bending. With the valence band edge that you measure, you can draw this level here, and you can again use UV vis absorption spectroscopy for the band gap and the cutoff for the vacuum level. So that gives you band alignment under dark condition, and you can also shine some light during your interface experiment to see the influence of light and to measure the photovoltage that you will create during your experiment. And you can see here that I observe photovoltage with XPS of 0.3 and a higher one during UPS. But that also gives me some band diagram under light, and that show me where does the photovoltage come from inside my material. So interface experiment is well known now, but you can study one interface at a time, meaning that this kind of experiment, it's already one day of experiments, and usually you don't want to let your sample overnight because you don't know what can happen. So yeah, usually you do one interface at a time. You need an integrated system, of course, and you can only study a thermal evaporation-based device. And we all know that spin-coated sample and thermal evaporated sample are quite different, have different properties. So you cannot study, let's say, all the solar cells that you can produce. So for that, we developed a third methodology inside our group, which is called the tapered cross-section photoelectron spectroscopy. I told you that the normal cross-section was too small, or let's say the lateral resolution of our machine was too high for a normal cross-section of your device. The idea is to create a tapered cross-section or a tilted cross-section in order to convert this 1 micrometer cross-section in a several millimeter cross-section. If you have a really, really low angle here, then you can really evidence all the different layers, and you can then measure the different layer of your stack just by doing a line scan with XPS, UPS, and again you can get some chemical composition, electronic structure of your device. So that leads to such kind of graphics. You can see here that you have 50 positions, and each position you can measure some core level spectra, some UPS spectra. And here we did a heat map, and you can see that the color indicates a strong intensity. So at the beginning, you have a strong signal of gold that then disappear. And then you have a strong intensity for lead iodine, indicated that here you have your perovskite sample, and at the end you can see the titanium dioxide layer, and you can identify all your layer across the tapered cross-section. And because you have this spectra, you can then do normal or standard data treatment, and you can extract some semi-quantitative information out of this measurement. So you can probe, for instance, the atomic concentration across your position, and you can see again, you have gold at the beginning, it disappears. You have a rising iodine or lead, and you can also do some stoichiometry. And what we found, was that when you go closer to this titanium dioxide perovskite interface, well, you can observe a bromine enrichment of your sample. So that was an evidence of, let's say, ion migration, but then it's still under debate if it's due to our polishing procedure or if it's really intrinsic to the solar cell. And you can, again, do some electronic structure analysis. So you can still look at this binding energy shift, as I discussed for the two previous stories. So if you look here, you see that gold is always at the same binding energy. So it's not so, it was quite expected because we ground the sample through the gold contact. So no shifts, a binding energy shift of 0, but then you can see here, for instance, that you will see binding energy going to higher 1. And so you can then draw such kind of diagram where you see then the lead going down. You can do that for carbon, you can do that for titanium dioxide, which give you evidence of bending inside a different layer of your solar cell. And you can see that you have quite a strong bending at the whole extraction layer perovskite interface. And the good thing with the tapered cross-section is that once you create it, you have access to every layer at the same time. So you can apply some voltage, you can shine some light on your material. And here you can see that when you put some light, you have a photovoltage and you see a shift to, again, lower binding energy. So you see a shift of 0.65 something electron volts, which leads you to almost flat band position of your different bands. And that again gives you the origin of the photovoltage, which is mostly at the all extraction layer perovskite interface inside your device. So we get this conclusion both from the interface experiments as well as from this tapered cross-section photoelectron spectroscopy. So in comparison to the interface experiment with the tapered cross-section, you can study all the interfaces at the same time. You need a well-defined method to create your tapered cross-section, which is not easy. And in principle, you can measure every system that are prepared outside, that are prepared with spin coating, and so on. So what I'm working on now, it's two things. The first one is, as I said, you need a methodology to create this tapered cross-section. So in the best of my knowledge, there are 3 papers out there on the so-called tapered cross-section, PES. 2 of them were about a sample tapered cross-section produced by manual polishing. And the third one, they used a drilling machine. And my work is to develop a methodology which provide more reproducible results and with the least possible induced surface defects. And the second thing is to answer the question, does the interface energetics that we measure here on the tapered cross-section, are they the same than on the normal cross-section? Do I have some difference due to the new geometry of the sample, or is it fully or are they the same and you can fully transfer all the knowledge that you get here to here? So to conclude and to summarize, I hope I convinced you that photoelectron spectroscopy is quite a strong technique to get chemical and electronic information at the same time. I hope that you also remember that it's a really surface technique, and due to that, and due also to the spatial resolution, we cannot measure directly the buried interfaces of a complete perovskite solar cell, but that's also the same thing for any, let's say, stack. And then you need to find some tricks, and I gave you 3 stories. One where we compare individual layers, but of course at the end you need to do some hypotheses on how the interfaces of these 2 materials should behave. And to overcome that, you can do either an interface experiment, which is already highly reported, but you also have some limitation to the material you can analyze and what you can say about it. And the third one, which is more new, maybe promising, but also still under development, is the tapered cross-section photoelectron spectroscopy, where you need to improve a bit the reproducibility and the understanding of the physics that is behind. And with that, I would like to thank you all for your attention. Thank you again to Rhiannon, Simon, and Vincent, sorry, for the opportunity. I also would like to thank my colleagues and co-workers. So of course, Max and Professor Bein in Munich for the 2D, 3D perovskite story. Clemens, Jan, and Uli Würfel at Freiburg, with who we get this SPP project, and all my co-workers in the surface science laboratory and my supervisors.